In data science, many of our most critical questions have binary answers. Will a borrower default? Will a patient survive? We have to take continuous variables, like a credit score of 720 or a patient age of 55, and map them into either 0 or 1. The simplest way to build that map is to just apply standard ordinary least squares regression, regressing our binary outcome directly onto our continuous variables. In this context, it is called the linear probability model. If we look at this scatterplot of credit risk, applying a straight regression line to binary data immediately breaks the math. As our continuous variables push toward the extremes, the straight line continues past the physical boundaries of our data, predicting values above 1 and below 0. A probability of 1.2 or negative 0.3 is mathematically meaningless. A straight line forces an infinite trajectory onto a strictly finite reality. The errors in this model also fluctuate wildly depending on where you look. If you measure the distance from our straight line to the actual 0 or 1 outcomes, the variance changes drastically along the x-axis, guaranteeing heteroskedasticity. Because those errors are not constant, standard statistical inference is compromised. The standard errors become invalid, which means the p-values we rely on to test our coefficients cannot be trusted without specific statistical corrections. Furthermore, real-world probabilities do not move at a constant linear rate. If a borrower is already at a 99% chance of default, a 10-point drop in their credit score cannot increase their risk at the same rate it would for someone sitting right at 50%. The probability must compress as it approaches the upper and lower boundaries. A straight line cannot compress. So, what structural transformation allows us to accurately model a binary outcome? To predict binary choice correctly, we have to abandon linear mapping completely. We must force the linear index through a nonlinear S-shaped function that strictly bounds our predictions between 0 and 1. The way we generate that S-shape starts by changing what we are actually measuring. We do not model the exact 0 or 1 directly. Instead, we model an unobserved continuous variable operating beneath the surface. Econometricians call this a latent variable, denoted as y star. You can think of it as a borrower's underlying propensity to default, or a voter's hidden utility for choosing a specific candidate. As this equation shows, this latent propensity is defined by our linear index plus an arrow term. We only observe a discrete 1 in our actual data when this hidden propensity crosses a specific threshold, usually set at 0. This means the probability of observing our target event is exactly equal to the probability that the error pushes the equation past 0. As the index increases, it shifts the distribution right, growing the area that crosses the threshold. Plotting this accumulated area on a graph perfectly traces out an S-shaped curve. In statistics, this S-curve is known formally as the cumulative distribution function, or CDF. We use this CDF as our link function. It serves as the mathematical bridge connecting our unbounded linear inputs to a strictly bounded probability between 0 and 1. But the exact steepness and shape of that S-curve is not arbitrary. It depends entirely on what specific probability distribution we assume for that initial hidden error term. The structural reality of a binary choice model is dictated completely by the assumed shape of an unobserved distribution. This requirement forces data scientists to choose between two dominant paths. Assuming logistic errors yields the Logit model. Assuming normal errors yields the Probit model. The mathematical distinction between these models comes down strictly to variance. The standard logistic distribution is wider, with a variance of 3.29, carrying heavier tails at its extreme ends. The normal distribution has a variance of 1, pinching down toward 0 much faster. Practically, this means a Probit model assigns slightly lower probabilities to extreme outlier cases than a Logit model does, simply because its tails are thinner. Because the underlying scales of variance are different, you cannot directly compare a raw Logit coefficient to a raw Probit coefficient. Looking at this rescaling formula, to translate between the two, practitioners rely on a standard scaling factor. Because of the difference in variance, a Logit coefficient will be roughly 1.6 to 1.8 times larger than a Probit coefficient estimated on the exact same data. Both models will predict probabilities almost identically in the center of your data, But their differing underlying variances force you to calibrate your coefficients differently depending on the model you deploy. When business stakeholders need to understand exactly how much a single variable impacts the outcome, the Logit model is overwhelmingly preferred. The Logit model uses a mathematical trick, the log odds transformation. While probability is nonlinear, the log odds is exactly linear. Exponentiating a Logit coefficient gives an odds ratio, a direct multiplicative effect size. A 0.05 coefficient translates to a 5.1% increase in odds. The Probit model lacks this clean interpretability. Because it relies on the normal cumulative distribution function, its coefficients do not represent odds. Instead, a Probit coefficient represents a change in the z-score of the latent variable. To make sense of this in applied work, analysts must convert Probit outputs into average marginal effects to see the actual percentage point change in probability. Regardless of whether you choose Logit or Probit, we still have to fit these S-curves to our data. And because the models are nonlinear and bounded, minimizing squared errors with closed-form algebra is impossible. This 3D surface represents our loss function, estimated using maximum likelihood estimation. Instead of drawing a straight line, MLE uses iterative algorithms to search the parameter space, finding exact coefficients that maximize the probability of observing the data present in our sample. In machine learning, this exact same mathematical hunt is known as minimizing binary cross-entropy loss. This loss function heavily penalizes confident, wrong predictions. If a model predicts a probability near 0, but the actual outcome is a 1, the penalty spikes, forcing the model to produce exceptionally well-calibrated probabilistic outputs. Logit provides a cleaner interpretation for stakeholders via odds ratios, but both architectures share the exact same computational heavy lifting of maximum likelihood estimation to bypass the limitations of linear regression. In applied data science, despite their theoretical differences, Logit and Probit will rank order your observations almost identically. The choice between them rarely comes down to predictive accuracy. It relies on domain-specific conventions and the need for advanced model extensions. Looking at these Python implementations side by side, Logit heavily dominates machine learning classification, medical risk scoring, and banking probability of default scorecards. Its odds ratio interpretability and cross-entropy optimization make it the standard for predictive pipelines. Logit also extends naturally into multinomial frameworks for unordered categorical choices. Probit, on the other hand, remains the structural workhorse for labor economics and political science, where latent utility maximization is the theoretical baseline. Because Probit operates strictly on a normal error assumption, it integrates seamlessly into larger systems of equations, where variables are assumed to be jointly normally distributed. This makes Probit explicitly necessary for advanced techniques like the Heckman selection model, correcting for sample selection bias by leveraging normal error distribution logic. We recognize the mathematical failure of straight lines on strict boundaries, adopted an unobserved error distribution to generate an S-curve, and deployed maximum likelihood to fit the data. The exact mathematical structure you choose, whether optimized for cross-entropy machine learning pipelines or latent utility economic models, ultimately defines and limits the analytical truths you can extract from binary data.